Welcome to Minukuu tutorials. In today's tutorial, we're going to look at how to perform simple linear regression in Microsoft Excel. So as you can see, I have my data set over here. This data set consists of, I think, 237 patients. And we have their gender, we have their ages, their height, as well as their weight. And we're going to perform simple linear regression, as I said. And by definition, in my own terms, simple linear regression is simply a linear model that we run to assess, or if you want to evaluate, the relationship between any two numeric variables. And this relationship has to be linear. So we try to inquire to know whether, and for instance, in our case, like I remember I said, any two quantitative, or if you want, numeric variables. If you have more than two numeric variables, or if you are going to carry out your regression on more than two numeric variables, then simple linear regression is not an option for you. You have to go for multiple linear regression. But simple linear regression is based on two numeric variables, such as height and weight. We could have done it between weight and probably age, or age and height. All these variables here are numeric, except gender, which is categorical. So, like I said, simple linear regression, we run this particular model to assess the linear relationship between any two given numeric variables. Okay, so without wasting my time, let me show you how to do it. So in order to run our simple linear regression model, we're going to need an add-in, an Excel add-in called, I think, Data Analysis ToolPak. This Data Analysis ToolPak add-in is usually in Excel, in most versions of Excel. I think from at least 2010 and above, you should have this ToolPak. But for the benefit of the doubt, we'll try to find out. And even if it exists, if you don't activate it, it will not show up. Usually when it exists and you click on data, you will find out that you have your data analysis ToolPak over here, as you can see in my case. But if I should uncheck it, for instance, let me show you, if I should hide it, you will not see it. So in case it's hidden, when you click on data and you cannot find the data analysis ToolPak over here, then let me show you how to let it appear. All you have to do is to come and click on File, then you come and click on Options. When you click on Options, you click on Add-ins, and you come and click on Go right over here. Click on Go, and then this small dialog box displays. And over here, you realize that Data Analysis ToolPak was already checked. That's why it showed up. If I should uncheck it, for instance, and I hit OK, it will disappear. So if I should click on Data, see a Data Analysis ToolPak is no more here. So in case you cannot find yours, please repeat this process by clicking on simply File, click on Options, click on Add-ins, come down and click on Go, check your Data Analysis ToolPak, hit OK. And so that when you click on Data, you can have your Data Analysis ToolPak. Now let's move on with the simple linear regression. To do this, to perform the simple linear regression, we simply click on Data, we click on Data Analysis ToolPak over here, Data Analysis, and then in this particular dialog box, we're going to select Regression. So you look for Regression. Okay, we have Regression over here, and then we hit OK. When we hit OK, with this dialog box displays for us to do our entries. So the first input has to be the Y range, so we simply click on this particular box over here, or this particular red point over here, red arrow, click over here, and then we're going to select our Y values. Now it's very important defining your Y and then your X values. The Y values, in other words, the Y variable or the Y column represents your dependent variable, and then the x variable represents your independent variable. The x variable is the predictor variable, is the one that predicts the value of your y. So that one is an independent variable, whereas the y variable is your what? Your dependent variable. So in our case, we are trying. We could decide to assess. To assess. In other words, whether weight, for instance, depends on height. So in this case, weight becomes our dependent variable, our y, and height becomes our x variable. So let's do that. So let's pick weight as our height, for instance. So we select all these values over here. Okay, select everything. Then we hit on this particular point, and then we click over here to select the x values. We could start from bottom, or we could move up to do it. There's no problem. Let me scroll up. Then this is our x values, which is the height. So we are trying to assess, or if you want to know whether there is any linear relationship between height and weight. When height increases, do we have an increase in weight? Or when height increases, do we have a decrease in weight? In other words, is the relationship, do we have an inverse or a positive linear relationship between the two? So we can perform simple linear regression to know, since these two variables are both numeric. Okay, so after you've selected your input ranges, it's important to click on label to tell R that, sorry, I'm talking about R because I've been using R, to tell Excel that your, what do we call it, the first row contains the row names of your variables. So you have to click on this particular page to tell Excel that the first row of your data contains the row names of your variables. Sorry, if you don't do this, Excel is gonna consider, for instance, all these, for instance, height. It will consider it as an input value, and it will give us an error because it's not a number. So you have to make sure you select that labels. Just select the box, check the box labels, okay, and after which you check confidence levels. That's if you want the confidence level to be 95, you just check it, that's the default. So we just simply check it 95, so that our risk of error will be 5%. And after which what should I say, what else can we pick? And now you have to decide if you should check this particular box. What that means is that you want the intercept or the constant to be 0. So we don't want it that way. Let's leave it. We want the true intercept, not not any assumption that the intercept is 0, unless you want it that way. And after which you come over here, and then for the input range, we select it later on. We have the choice. We could either place all the results on the same page, on the same sheet, or we could put the input range on a new worksheet. So we could just leave it this way, and after which we can select the output range. We'll do that later on, but let's look at the plots, graphs that we would like to plot. So we may want to plot the graph of the residuals, which is the difference between the y values, the individual y values, and their predicted values by the model. That's what we call the residual values, the difference between the individual y values, and then their, what do we call it, their predicted, their model predicted values, and then, or the fitted values, okay, if you want it that way. Differences between fitted values and individual y values gives us, or individual values, not only y values, gives us our residuals. We can have x residuals, we can also have y residuals. I don't want to talk too much, but what else can we pick? We can also pick, if we want to have the standardized residuals, The standardized residual is simply the residual divided, each residual value divided by the standard deviation. So we could pick it if we want, and we could also add residual plots if we want it, and then line of best fits, so that we can have our regression line. Let's pick that one too. And after which, if we want, we could also pick a normal probability plot. Normal probability plot is for evaluating the randomness of our data set, whether our data is is randomly distributed or not. So we could check it, and then the residual plot here will help us also analyze the quality of the model, in terms of different in terms of what we call it. Let me just hit OK so that we have the graph, and then we'll try to do the interpretation. So let's hit OK. If we don't want any other thing, we can uncheck it later on. But it's important now to select the output range. So we make sure we click on this particular button here. If we want to put it on the same page, then we click on this button and we select the output range. If we don't want to put it on this page, then we can put it on a new worksheet. But I would like to place it here so that everything will just be together. So I'll click over here, and then I'll click here and go select a strategic place to put it. I could put it over here so that it will be very close to the data set, and I just click over here and hit OK, and bam, we have our results over here. And now we're going to see how we can interpret these results and everything. So let me try to create some space and make sure the results are bold and clear for proper interpretation. Okay, I want everything to be clear. I'm gonna enlarge some of these columns. Okay, perfect. At least I think it's not bad. Now after we have this, I hope you can see properly, else I can try to bolden it a bit, so to make the results a little bit bold. Okay, everything is a little bit bold right now. Good. Okay, before we interpret, let me work on the graphs too before we interpret the results. So the graphs, we have different graphs over here, and well, first of all, let's interpret the results, and we'll now come to the graphs and I'll interpret the graphs. So now the results, it first of all gives us the summary output, and the summary output here, that's our regression coefficients, and then what we also call the multiple R squared, or the coefficient of determination. So over here, the coefficient it has given us a standardized, we have the multiple R and then R square here. Okay, I think either of them, for instance in R it only gives us multiple R, but over here it gives us R squared. R squared here represents the coefficient of determination, which represents the percentage of variance of our dependent variable, in this case of weight, that can be explained by the variance of the height, or the independent variable. Now is the percentage of the variation in the dependent variable, which is weight, that can be explained by the variation in the independent variable, which is the x. or our height in this case. So in this case, we have 60% because this is in decimal. So if you multiply by 100, you get 60%. It means 60% of the variation of weight can be explained by what? By change in height, of one variation in height. And after which, what we also have to note, it also gives us the number of observations. I told you earlier on that we have 237 patients. And what is important over here is to come to ANOVA. ANOVA here, you can interpret the results in different ways, you know. Either you can base on analysis of variance here to determine whether the slope is is significantly greater than or less than 0 or not. Now, where is first of all the slope? When you look at you have to look at your regression coefficients, right? For when you are looking at analysis of ANOVA or the F test over here, it's actually based on the residuals. You know, it's based on your residuals over here that we have this statistic. So you can interpret, just go ahead and interpret the p-value. See that the p-value here is less than 0.001 self. So what that means is that there is a significant relationship between the, what do we call it, between our height and weight. So based on the residual analysis, we could conclude, but it's important to look at the slope first of all. So let's just leave this one hanging, and let's come to this the second table, which is the table of the coefficients. So the coefficients here, we have our intercept, which is minus 132.9 something, and the intercept is not even really having any significant meaning unless you want to interpret it for any reason. What's more important here is the slope, or the beta. So our slope is 3.8, which means it's greater than what? 0. When the slope is equal to 0, it means there's no any relationship between your x and y values. In other words, weight that does not depend on height in our case. But since the slope is positive, it means there's a positive relationship between the two. If the slope were negative, then it means there is a negative relationship between the two. So since the slope is 3.8, it means there's a positive association or relationship between height and weight. But now, even though the slope is greater than 0, you still need a statistical test to prove whether it's significantly greater than 0 before you can conclude that there is a positive linear relationship or association between the two quantitative variables. So this can be verified by the t-test. You know, so the t-test of the slope here gives us a p-value, right? And if I should move over here, you see our p-value here to be, what is our p-value? Okay, this is our p-value over here, and as you can see, the p-value is actually less than 0.001. So it's highly significant. What do you call it? It's less than 0.05 in the first place. This the primary condition is that it should be less than 0.05, and when it's less than 0.001, it means it's even highly significant, statistically significant, you know. So this affirms the fact that there's a positive relationship between the two variables. And then it's also important to look at the confidence interval of your slope, because sometimes p-value can be significant or not significant. Meanwhile, for instance, p-value can be significant, meanwhile the confidence interval that contains contains 0. If the confidence interval contains 0, then there's no need, even if the p-value is significant, shows that even if the p-value is less than 0.05, we still have to conclude that there is no any relationship between the two variables. But in our case, you know, the confidence interval actually affirms the fact that the p-value is less than 0.05, because our confidence interval does not contain 0. You see that the lower limit is 3.4 and the upper limit is 4 point something. It doesn't contain 0. I think this marks the end of the interpretation of the results. Now we have our residuals over here. You know, the residuals, like I explained to you, is a difference between what for each person. The residual value for each person is simply the initial y value of the person minus the predicted value of the model. So this is what we have over here, you know. And then the standard residuals is simply what each residual divided by the standard deviation of all the residuals. So if you want to verify this, we can quickly do this. Come over here, come down, and come and calculate the standard deviation of your residuals. You see, so you simply say equal to, and you say, for instance, standard deviation, okay. So we're going to calculate the standard deviation of, standard deviation of our residuals, right? So let's select all these values, and then let's close the brackets, and then we hit enter. So we have our standard deviation to be what? 12.28. So if you come and pick, for instance, for the first value, if you pick 12.28 here, which is the residual value, if you pick 3.028 divided by 12 so if we should say, for instance, if I should say this particular cell here divided by 12.28, you see that it gives us this particular value that we have over here, 0.24 something. So the standard residuals is simply the residual values, individual residual values divided by the standard deviation of the residual values. And what else can we look at? We also have the probability, whatever, outputs. This, I don't really see the need interpreting all this. So let's move on. Let's look at the graphs quickly. So, like I told you, what's more important for your output is simply come and look at your what do you call it, your beta. Make sure that try to know whether it's is it less than 0 or not, is it greater than 0 or not, or is it equal to 0. If it's equal to 0, then it means there's no relationship. But how do you know? So you have to look at the confidence interval to make sure that the confidence interval does not contain 0. You also look at the p-value to make sure that p-value is significant. If it contains 0, it's not a crime. You're going to conclude that there's no any relationship. The aim is not to look for a relationship. We never knew whether there was a relationship between the two variables or not. That's why we performed the test. So this is the interpretation. Now let's look at these plots over here. This probability plot here, it helps us. This is more or less like the QQ plot that we often have in R. Usually when all these plots, for instance, let me show you something. If I should select the graph, for instance, this particular graph, just select it this way. You can enlarge it a bit, select it this way, and then you come and click on design. When you click on design, come and click on this particular portion, quick layout, and then you come down and select this particular one, and you have this black line over here. Normally when all these points, or when majority of the points are located on this line here, then we say your data follows a normal distribution. You see, but so this is a plot. This is actually used to access the relationship, to access the quality of your regression model. So in our case, it's actually subjective, so you have to look at it and interpret it in your own way. In our case, you can see that the most of the values are lying on this particular line, straight, like this line that of best fit that we've drawn. So it's actually a plot of the weight and then the sample percentiles. And as we can see, majority of the points are lying on it, so we could say our sample is randomly distributed. Not perfectly random, but at least it's very good. Majority of the points are lying on the line. Now, having done with this, let's look at the other graphs that I now try to interpret each and every one of them. This is actually your line of best fit or your regression line, but it's not very nice. We're gonna make it better. Let me go down and put this one down. Okay, so let's look at this one too. This one here is your height plot of height on residuals, and this one doesn't really give us more information. It's also about the quality of the model, right? And then it also tells us about the quality of the model. So what do we say? If we look at this, you see that it has given us the residuals. We have the zero line over here, and this zero line, all the individuals that will be found directly on this particular zero line, what it means is that these individuals on the regression, let me actually draw the regression line for you to see something. Let's draw the regression line. Let me try to enlarge it furthermore. Okay, now it's a little bit better. So we have our two graphs here. Let me go up a bit. Let's enlarge this one to a bit. Good. Let me enlarge them. Enlarge this one furthermore. Okay, nice. So first of all, before we interpret this other one, let me interpret this particular one here, which is the regression line. So you see that it has actually drawn we have, if you look over here, we have the weight, which is in blue, plot of weight and on height. This is the blue. These are the blue points over here. These are your individual values, and then the line of best fit is this particular yellow line here, but it's not clear, so I will use a straight line to beautify it. So how do we get our straight line? Simply select the curve, your graph, and then click on design once again. Come and click on quick layout, and then select this particular line. So we have our line of best fit cutting across the points, So what do we say? And it has also given us the equation of the line very beautifully. Now what I was trying to explain is that you see that if we should trace down, the line is actually going to cut the intercept at negative something here, and then if we should observe critically, we will see that there's actually a linear relationship between height and weight. You see that the points are actually together and along the regression line. So we have I wouldn't say a perfect line of best fit, but not we have, I'm trying to say most of the values are close to the line of best fit, right, or the regression line. So it confirms the fact that there is a very significant positive relationship between height and weight. Now all the points that are found on this particular on the line of best fit, these points will be found on the zero line of your residuals and height plot over here. These points are these ones over here. They'll be lined they'll be lined strictly on the zero line over here. These particular yellow points are the points that are lined strictly on the zero line here, strictly on the zero line. Why? Because their residuals are equal to 0. When a point is found lying straight on an individual, we say an individual's residuals is equal to 0 when the individual point lies directly on the regression line. When it lies directly on the regression line, it means the residual will be 0. But when somebody lies outside the regression line, for instance, we pick this particular person who is lying here, if we should trace, let me pick this one for instance, this one over here. If we should trace over here, we get something like 170. And then if we should trace to the regression line and then trace over here, we get like 140. So 170 minus 140, we have like 30 difference, and this is our residual. But somebody who is lying straight on the regression line, if we trace, for instance, somebody who is here, we get 120. If we trace, it's already on the regression line, so 120 minus 120, the residual is 0. So what is the purpose of this graph? This graph helps us. What does it do? It helps us also evaluate the quality of our model. Remember, we looked at the first graph, which has to do with randomization. Or if you want the randomness of your, the randomness of your sample distribution. In other words, when you have a normal sample distribution, then what that means is that I told you that all the points will lie on the curve, on this particular curve. And then I'm also trying to let you understand that this other graph, which is a plot of height on residuals, in other words, the x on the residuals, also evaluates the quality of the model. The first case has to do with, or the first criterion that this graph helps us evaluate is what? Is that it helps us detect non-linearity. When we talk of non-linearity, is the situation first of all, when we talk of linearity is the situation when we have the points, or for instance, when we have the point randomly bouncing, randomly bounce across the line. So you see that our straight line is here, and it's like the points are randomly dispersed across the line. Even though, so in this case, we can say, even though all these interpretations are actually subjective, so I wouldn't say you should just hold on to it as if you can have a subjective. But in our case, you can see that there is we cannot we cannot talk of any the model is best when there is linearity, so when the points are randomly distributed across the 0 line. So in our case, the points are randomly distributed across the 0 line, and then we could also realize that most of the people have a value of around 50 something. That's why all the points are located at the far right hand side of the curve. So that's what we have to talk about concerning linearity. So we are saying that it's relatively linear. And then to talk about another issue or another important criterion that this particular curve helps us evaluate is what? Is the equality of variances criterion. And when do we say we have equal variances? When the points form like a band, when the points are very close to each other, and then they surround and they are very close to the 0 line. In this case, we say their variances are equal. So it's more or less like the differences between them is very tight. So we talk about equal variance of our residuals. But in our case, the points are also very close to each other, but we actually have some extreme values, and they don't really form a band along the 0 line. So we cannot really talk about a perfect what do we call it? We cannot really talk about a perfect equality of variances here, but relatively is good. We say the model is best when we have equal variances, when we also have linearity, as I explained earlier on. And the third criterion that this curve can help us figure out is the outliers. So we have a couple of values like these ones over here, which are outliers. You see that they are far apart from the rest of the values. And when interpreting our regression results, we could decide to ignore such individuals in order not to let them affect our results. So this marks the end of our tutorial on simple linear regression on Excel. If you have any question, please do not hesitate to ask, and I will respond to you if I know the answer. Hope you found this video interesting. Please subscribe.